So today we're going to be looking at geometric series, the sum of geometric sequences. And I thought we could start off with finding a sub 8 in this geometric sequence. Please take a moment now to find a sub 8, given that a sub 3 is 2/9 and a sub 6 is 2 over 243. Okay? Pause your pause your video, come back when you're done. Welcome back. So I'm going to do 2 over 243 equals a sub 1 r to the 3 minus 1, which is r squared. I'm sorry, I put in the 6 there. So 6 minus 1 is 5. And then 2 over 9 equals a sub 1 r to the 3 minus 1 is 2. So I've got my two equations with two unknowns. I'm going to divide one equation by the other. Over here on the right, I see the a sub 1's cancel. And r to the 5th divided by r to the 2nd would be r to the 3rd. And then over here I have 2 over 243 divided by 2 over 9, which is the same as 2 over 243, times 9 over 2. The 2's cancel, and in fact, 9 goes into 9 once, and 9 goes into 243 27 times. So I get 1 over 27. When I take the cube root of both sides, I get r equals 1/3. And now that we know what r is, we can plug that back into one of these equations, it doesn't matter which, to find a sub 1. So 2/9 equals a sub 1 times 1/3 to the 2nd. Or 2/9 equals a sub 1 times 1/9. If I multiply both sides by 9, I get a sub 1 equals 2. And therefore my rule is going to be a sub n equals 2 times 1/3 to the n minus 1. I'm looking for a sub 8, so 2 times 1/3 to the 8 minus 1, or 7. So 3 to the 7th is 2187. So we're going to have 2 over 2187. That's my favorite answer, but of course you could always decimalize it and write an approximation 0.00914494747. I'd rather write that. Okay. So there's our bell work. Welcome back. Let's talk then, since we know how to find geometric sequence geometric sequence values. I thought we could look at the geometric sum. Okay, and I want to take a few minutes to derive this formula. This is for you, Nathan. A sub n equals a sub 1 r to the n minus 1. All right, so I want a sum formula, not a formula that figures out the value of the nth term, but actually a formula for finding the sum of all the terms. So let's see what we can think about here. A sub 1, a sub 2 would be a sub 1 times r to the 1st. A sub 3 would be a sub 1 times r to the 2nd. And we could then add up all of these, right? So S sub n would be a sub 1 plus a sub 2 plus a sub 3, all the way out to a sub n. We're going to add them all up. But now I can replace a sub 2 with this, and a sub 3 with this. And so my new statement, a sub n equals a sub 1 plus a sub 1 r to the 1st plus a sub 1 r to the 2nd. Then I would have a sub 1 r to the 3rd, and so on, until I came out to, now notice, this is the 2nd term. This is the 3rd term. This is the fourth term. So I want here, the last one would be a sub 1 r to the n minus 1. That's our rule. So I put in a 4 there, and I end up with 3. Great. So that's what I'm adding up. Now, I want to do something that is not very intuitive. I want to multiply both sides of this equation by r. So if I multiply by r here, I just get r times the sum of n things. And over here, when I multiply by r, this is going to have an r to the first. This will be r to the second. This will be r to the third. This will be r to the fourth. And when I multiply by r here, that's going to add 1. And so I just have r to the n over here. Okay, now what can we do? Well, so here's the thing. I've got this r times a sum of n things. So what I'm going to do now is subtract from this. I want to subtract from this s sub n. And conveniently, s sub n is here. So a sub 1 plus a sub 1 r plus a sub 1 r squared plus a sub 1 r to the third, and so on until I get to a sub 1 r to the n minus 1. Okay, and we're going to subtract. Now, when I subtract, I can see already that these will cancel, and these will cancel, and these will cancel, and that this would cancel, and that these would cancel. And so I'd be left with this, and I'd be left with this. And I'm subtracting this. And so I'm going to have then, as my expression, r times s sub n minus s sub n equals a sub 1 r to the n minus a sub 1. Okay, so what can we do here? Well, on this side, I'm going to factor out an s sub n, because that's the thing I'm trying to solve for. And on this side, I can factor out an a sub 1 and get r to the n minus 1. Now, I'm trying to get this by itself, so what I need to do is to divide both sides by r minus 1. Boink, boink. So we get s sub n equals a sub 1 r to the n minus 1 over r minus 1. And there's our formula. Yeah, that's our formula. Often, though, in our book, what we're going to see is a sub 1, 1 minus r to the n over 1 minus r. And if I divide top and bottom by negative 1, that's how I get that. Okay? So there's our sum formula. So if I want to find s sub 10, the sum of 10 things, s sub 10, given that a sub 1 equals 1, and a sub 2 equals 3 halves, and a sub 3 equals 9 fourths, and 27 eighths, and so on. And we're adding these all up now. We're looking for a sum of a geometric sequence. And I know it's a geometric sequence because I can always confirm the r value. 9 fourths divided by 3 halves is 9 fourths times 2 over 3, which is 3 halves. And if I take, so that was this one divided by this one. If I do this one divided by this one, I get the same 3 halves. So I know that r is 3 halves. Okay, so let's plug in what we know. We know that a sub 1 is 1. We know that r is 3 halves to the 10th, because we want s sub 10, or better yet, that's s sub n, and this is s sub 10, minus 1 over 3 halves minus 1. Okay, so pull out my calculator, and I want 3 halves to the 10th power minus 1, and I'm going to divide that by 3 halves minus 1 half is 1 half, and so I get the sum would be 113.33000781. We can try and turn that into a fraction, and I get, let's have a little light here, 58025 over 512, if you wanted the exact value. Okay, so that's how we use our sum formula. That's what our sum formula is and how we use it. So again, that sum formula is a sub 1 r to the n minus 1 over r minus 1. Of course, we'll also see it as a sub 1, 1 minus r to the n, 1 minus r. Either one works fine, I believe. Okay, so 256 plus 192 plus 144 plus 108 plus and so on. And again, I'm looking for S sub 10. Is this geometric? Maybe it's arithmetic. So if I do 108 minus 144 minus 108, I get 36. That's that difference. We went down by 36. But here, if I subtract 36 from 192, I'm not going to get 144. 192 minus 36 is 156, not 144. So this is not arithmetic. But is it geometric? Well, let's test. 144 over 192. And I end up with 3/4. And then if I do 192 over 256, I also end up with 3/4. So this is geometric, and I can find the sum of these first 10 terms by using our geometric sum formula. We found out that r was 3/4. Since I'm going to be plugging it into the calculator, you can certainly use that 0.75. There's no problem with that. And here's our a sub 1. So S of 10 equals 256, 0.75 to the 10th minus 1 over 0.75 minus 1. All right, so on the bottom, we're going to have negative 0.25. Wonder what we're going to have on the top. 0.75 raised to the 10th power minus 1. So I get 256 negative 0.943686485 and on the bottom negative 0.25. So let's take that numerator and divide it by negative 0.25. And then let's multiply by 256, and I get 966.3349609. If I convert that to a fraction, I have 989527 over 1024. I show you this fraction one because often in the back of the book they give us fractiony answers, not these decimally answers. This is a great decimal approximation of this actual value. Fabulous. So that's how this works. Why don't you do a couple practice problems now using this formula? How about we have 1 minus 0.1 plus 0.01 minus 0.001 and so on. And we still want S sub 10. Find S sub 10. Pause the video, give it a try. Okay, welcome back. The first thing I need to do is identify the elements that I need to use this formula. I need a sub 1, great, that's 1. And I need r. R is not given, obviously, I'm going to have to find it. But I know that r, the common ratio, is a sub 3 divided by a sub 2, or a sub 2 divided by a sub 1. And since they already tell me that this is geometric, I don't have to test a bunch of them. I could just do a sub 2 divided by a sub 1. So negative 0.1 divided by 1 is negative 0.1, or negative 1/10. So there's my r value. Okay, so then if I write the sum of 10, I'm going to have 1 times -1/10 to the 10 minus 1 over -1/10 minus 1. Okay, so -0.1, oopsie, got to put that in parentheses, -0.1 in parentheses raised to the 10th minus 1 divided, which is -0.999993369 369 okay, over -1/10 minus 1 is -1.1. So if I do -0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divided by -1.1, I end up with 90.90, 90, 90, 99. Okay, and as a fraction, doesn't convert. Okay, so that's my sum, the sum of the first 10 terms. Positive. The signs are alternating, but the biggest value is positive, so my answer is positive. Okay, and what would we do with something like this one? Square root of 2 minus 2 plus root 8 minus 4 plus, and so on. All right. So if I do -2 divided by root 2, and then I rationalize, I have -2 root 2 over 2, or -√2 equals my r value. Let's confirm that by doing square root of 8 divided by -2. Remember, square root of 8 is 2 times 2 times 2, so we've got 2 root 2 over -2, or -√2 for our r value. We see a sub 1 over here, and so the sum of 10 things would be square root of 2, that's a sub 1. We have our r value, -√2 to the 10th minus 1 over root 2, that's -√2 minus 1. All right, and then when I do that on the calculator, negative square root of 2, and I'm actually going to store that because I think I need that again. So I want that value raised to the 10th, and then subtract 1, and that gives me 31, and then on the bottom I have x minus 1, -2.414, 213562. So 31 divided by that answer, and I end up with -12.84062043. Negative though. Did I make a mistake? Shouldn't this be negative? That's positive. -1 is positive. And on the bottom, that's negative. I get negative. Ooh, did I multiply times that root 2? No, times square root of 2. Oops. Times square root of 2. And so I get -18.15937957. I find that a little troubling because my biggest value, oh, this is smaller than that. Oh, and this is smaller than that. So the positives are all smaller than the negatives, which is why my total of 10 things is a negative number. Okay, great. So what about not s sub 10, but s sub infinity? What if we let this sequence run on forever and we added up all the terms? Well, it turns out that if we let n head to infinity, let's take a look at what happens to our formula. R to the, in fact, I want to do that other form here. R to the n over 1 minus r. Okay, so, if I plug in an infinity here, if r is a big number, then that's a big number to the infinity. And so this is going to be infinitely large. So for example, if we have r equals 3 and a sub 1 equals 1. So 1 minus 3 to the infinity over 1 minus 3. Well, 3 to the infinity, that's infinity. So I have 1 minus infinity on top and negative 2 on the bottom. So 1 minus infinity. You could also think of that as negative infinity plus 1. Nobody's going to notice that extra 1 there. And so we end up then with negative infinity divided by 2, and infinity divided by 2 is still infinity. So this turns out to be an infinite sum, like the value of this sum is infinity. So there's not a lot of value in doing the sum of an infinite number of terms when r is bigger than 1. But what about situations where r is between 1 and negative 1? So now we have something like an r value of 1/2. Okay, so let's do a sub 1 equals 2 and r equals 1/2, and our sum formula would now be 2 times 1 minus 1/2 to the infinity over 1 minus 1/2. Okay, so that's going to be 1/2 on the bottom, and then we flip and multiply, so this is 4, 1 minus 1/2 to the infinity. Now, about 1/2 to the infinity. So that's a lot of zeros there. Think about it this way. How can I explain this? 1/2 to the infinity. 1/2 to the infinity. Yeah, it's hard because I know you want to say that 1 to the infinity over 2 to the infinity is going to be 1 over 2 to the infinity. Sure, let's do it that way. 1 pizza, 2 to the infinity people show up for dinner. How much pizza do you get? That's 0. So this over here is 0. And so we now have 4. So when r is between negative 1 and 1, I can actually find an infinite sum. In fact, with our infinite sum formula, sum of n a sub 1, 1 minus r to the n over 1 minus r, when r is between 1 and negative 1, this part here always becomes equal to 0. And so we end up with a sub 1, 1 minus 0 over 1 minus r. 1 minus 0 is 1, and 1 times a sub 1 is a sub 1. And there's our formula for the sum of an infinite number of things in a geometric sequence. Now, this sum of an infinite number of things in a geometric sequence only works when r is between -1 and 1. If r is bigger than 1, that sum of an infinite number of things will be infinity. But when that r value is between -1 and 1, this sum of an infinite things actually converges. I mean, let's take a look at what we're thinking about here. So that last problem where we started off with 2 and our r value equaled 1/2, so this was +1, +1/2, +1/4, and so on. If we add this up forever, our geometric sum formula, sum of an infinite, says a sub 1 over 1 minus r. So that's 2 over 1 minus 1/2, which is 2 over 1/2, or 4. So the sum of adding this up forever will be 4. And I think it's very interesting that I have the first 3 3/4 here in the first 4 terms. So aside from the first 4 terms, the rest of the infinite number of terms that go on forever, when we add them all up, they'll add up to exactly 4. And I think that's a beautiful piece of math magic. Okay, so find S sub infinity if 256 plus 192 plus 144 plus 108. Okay, so please find the sum of those infinite things using that sum formula. As a reminder, S sub infinity is a sub 1 over 1 minus r. Okay, welcome back. A sub 1 is 256. And we found r for this sequence already. 192 over 256 was 3/4. So I've got 1 minus 1 3/4, which is 256 over 1/4. And that's the same as 256 times 4, which is 1024. 1024 will be the sum of the infinite number of terms in this sequence, which I think is really, really amazing. That A, we can find a sum, and that B, the sum can be that like finite number, right? It's not, finite number. Okay, so let's go. How about you do this one? 6 plus 3 plus 3/2 plus 3/4, and so on. Find the infinite sum here. Why don't you give that a try? Okay, did you get 6 over 1 minus 1/2 is 6 over 1/2, or 12? I hope so, because that's our answer here. Can I do the same thing with this infinite sequence? Find S sub infinity, given that 7 plus 14 plus 28 plus 56, and so on. Can we add up that infinite sum? Why don't you give it a try? Come back in a minute when you're all done. All right, so what I notice here is my r value, 28 over 14, is 2. And that's bigger than 1. When r is greater than 1, the sum of an infinite number of things is infinity. So I'm not going to be able to use this formula. I'm just going to know, because r is greater than 1, that I have a sum of infinity here. Okay. So, sigma notation. Sigma notation is the notation that we use for sums. So, let's go back and have a little conversation about sigma notation. 7, 11, 15, 19, and so on. I could say with this, if I wanted to add this up, if I wanted to write this in sigma notation, I could say add it all up. But I might want to say instead, this goes up by 4 each time. Plug in a 1 for the first term, get 7, so I must have to add 3. This is the rule for this arithmetic sequence. And I could say start with n equals 1 and go someplace. I don't know, maybe we want the sum of the first 9 things. So that would be s sub 9. Now we know that we can use our arithmetic sum formula, s sub 9 equals, or s sub n equals n over 2, a sub 1 plus a sub 9. And so we would plug in a 9 over 2, a sub 1 is 7. I need to find a sub 9. I need the rule to do that. 9 times 4 is 36, plus 3 is 39. And so I have 46 9 over 2 times 46, or 23 times 9. So 180 plus 27 is 207. So I can describe the sum of all these things by using this shorthand notation. And then once I see this familiar shorthand notation, oh, sigma is a sum, I can just jump to my sum formula. Okay, so the same thing's going to happen with geometric sequences. We're going to see I equals 1 to 9, 2 to the I minus 1. Now, this is our geometric sum. I know it's geometric because I see a little exponential thing here. I knew that this was arithmetic because I saw a linear thing here. So I used the linear sum formula here, the arithmetic sum. Here I need to use the geometric sum because I see this exponential. Remember that sum of n terms for geometric is a sub 1, 1 minus r to the n over 1 minus r. Well, what's our a sub 1 and what's our r? A sub 1 is what I get when I plug a 1 in here. So 1 minus 1 is 0. 2 to the 0 is 1. And then our r value is 2. And our n value is this number here. So I want 1 minus 2 to the 9th over 1 minus 2. Okay, so 2 to the 9th is 512. So 1 minus 512 is negative 511. And on the bottom we have negative 1. And so we get 511. If we add up the first 9 terms in this sequence, we should get 511. Now, we could always, and I definitely don't recommend this, if you want to know s sub 9, you could find s sub 1, s sub 2, s sub 3, s sub 4, s sub 5. Look, I'm already bored all the way up through s sub 9, and then add them all together. I'm sorry, we'd find a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5 plus sub 6. Oh my god, I'm already too tired. Plus a sub 9. And to find a sub 1, we plug a 1 in here. To find a sub 2, we plug a 2 in here. 2 minus 1 is 1. 2 to the 1 is 2. And to find a sub 3, I plug a 3 in here. I get 2 squared, or 4. And then I plug in a 3 up here. I'm sorry, a 4 up here. I get 2 to the 3rd, which is 8. And I keep going until I end up with 2 to the 9 minus 1 is 8. And so then I could add up all these by hand. But really, why? Why? Why not just use that sum formula, a sub 1, 1 minus r to the n over 1 minus r? Okay, so there's our sigma notation. Let's see if you can do one. How about I equals 1 to 6 of 32, 1/4 to the n minus 1. Oops, I minus 1. I guess I'll call this n so that this can stay n. Okay, so find this sum. Remember, in order to use our sum formula, We need a sub 1, we need r, and we need an n value. So what do we see? Here's our n, here's our r, and what about a sub 1? Well, if I plug a 1 in here, 1 minus 1 is 0, 1/4 to the 0 power is 1, 1 times 32 is 32. So I have 32, 1 minus 1/4 to the 6th over 1 minus 1/4. Okay, so 1/4 to the 6th power, 1 minus that answer, and then I want to divide that by 1 minus 1/4 is 3/4, and then I want to multiply that by 32. And I end up with 42.65625. Does that convert to fraction nicely? Yes, it does. 1365 over 32. All right. Now, I will say that these aren't so bad. You know, the sigma notation is a little disorienting, but it's just a way of saying I want to add up this geometric sequence in shorthand. So we know that we can find a sub 1 by plugging in a 1 here. We know that that's our r, and we know that this is our n. Now, sometimes, though, the formula is written like this. N equals 0 to 3 of 5 times 3 to the n. So let's plug these values in. 0, 3 to the 0 is 1. 1 times 5 is 5. And then I'm going to plug a 1 in. 3 to the 1 is 3 times 5 is 15. Then I'm going to plug a 2 in. 3 squared is 9 times 5 is 45. And then I'm going to plug a 3 in. I get 27 times 5, which is 2, I don't want to do that in my head, times 5, and I get 135. Oh, sorry, times 3, not times 5. 135. And so that's with this sequence. The problem is that when we want to say, when we want to use S sub n equals a sub 1, 1 minus r to the n over 1 minus r, that's based on this sigma, n equals 1 to some number of r to the n minus 1 power. This isn't n minus 1, and this isn't 1. So we want, when we see this form, to rewrite it in this form so that we can use this formula. All right, so I'm using this to generate this, and from this I want to generate my rule. I see a sub 1 is 5, and I see that r is 3, because 15 divided by 5 is 3, and 45 divided by 15 is 3, and so I know my r is 3. And so then I could say a sub n equals using a sub 1 r to the n minus 1, my formula would be 5 times 3 to the n minus 1. Okay, so that was the oh, right. So what I'm going to say here is that when I'm given this, 5 times 3 to the n, that's going to be the same as n equals 1 of 5 times 3 to the n minus 1. But now, what happens to this number? Well, this number is 1 less than this. So this number must be 1 less than this, right? Because I'm adding up 1, 2, 3, 4 terms. So my n is actually 4 in this problem. Okay. So first comes the rewriting, and now I can move on to using that sum formula, okay? So that sum formula would then be a sub 1, which would be 5 times 1 minus 3 to the fourth over 1 minus 3. 3 to the fourth is 81. 1 minus 81 is negative 80 over negative 2 times 5. I get 40 times 5, or 200. So the sum here would be 200. So let's try rewriting another one or two of those. The sum n equals 0 to 15 of 2 4/3 to the n. So this isn't 1, and this isn't n minus 1. So the first thing we need to do is turn this into 1 and 2 to the 4/3 n minus 1. But if this becomes 1, we added 1 to this, we want to add 1 to this and get 16. I thought I subtracted 1 before. No, I went to 4. Yes, okay. So we use our shortcut formula now. The S of 16 things will be a sub 1, which is 2 times 1 minus 4/3 to the 16th over 1 minus 4/3. Okay, so 4 divided by 3 raised to the 16th power, 1 minus that answer, and then I want to divide that by negative 1 divided by 3. Don't forget to multiply by 2 at the end, and I end up with 592.647311. And does that convert nicely to a fraction? No, not for my calculator. Okay. So let's do one more of those, and then we'll move on. Okay. Sigma n equals 0 to 20 of 500, 1.04 to the n. So I can rewrite that sigma n equals 1 to 21, 500, 1.04 to the n minus 1. Now, this might look like, r 1 plus r to the n. P equals A. Remember our exponential growth formula for annual growth. And we could find the sum of all that exponential growth by using our shortcut formula, 500, 1 minus 1.04 to the 21st over 1 minus 1.04. And so I end up with 1.04 to the 21st, and then I do 1 minus that, and then 1 minus 1.04 is negative 0.04, so I want to divide this answer by negative 0.04, and don't forget at the end to multiply by 500. So I end up with 15984.60086. All right, and I guess you could say if you were getting 4% annual interest and starting with $500, after 21 years, you'd have $15,984, and that'd be really nice to have. Okay, so can you rewrite this into sigma form? 7 plus 14 plus 28, and so on, until we get out to 896. Well, at first I think, no problem, 14 divided by 7 is 2, and 28 divided by 14 is 2, and so I know that r equals 2, and I've got my a sub 1, and that sounds fabulous. So in sigma form, I'm thinking a sub 1 times 2 to the n minus 1, n equals 1 to, uh-oh, I don't know this number. I know this is the first term and the second term and the third term, but I don't know what term number this is. And that's the number that has to go here. So what I'm going to have to do is I'm going to have to take this rule that I built, and I'm going to have to set it equal to 896. So we'll divide both sides by 7. 896 divided by 7 turns out to be 2 to the n minus 1 equals 128. And last semester in pre-cal, I said, look, you're trying to solve this exponential equation. Why don't you write both sides so that they have the same base? So 128 is 2 to the 7th. Because if the bases are the same and the terms are equal, then the exponents have to be the same. And so n equals 8. Now that I know what n equals, I can write my sigma, n equals 1 to 8. And here's my answer. Okay? So, why don't you do this one? 2 minus 1/2 plus 1/8, and so on until we get out to 1 over 20, 48. This is what we want to write in sigma notation. So, find a sub 1, find r, find n, and then write the sigma notation. Come back when you're done, or when you're stuck. All right, welcome back. So the first thing I want to do is find r. So 1/8 over negative 1/2 is 1/8 times negative 2 over 1, or negative 1/4. So, and let's just confirm that with negative 1/2 divided by 2. That's negative 1/2 times 1/2, or negative 1/4. So I've got an r value. I've got an a sub 1 value. R is negative 1/4. A sub 1 equals 2. There's the value of our first term. But I don't know how many terms I've got. So I'm going to build the rule. A sub n equals 2 times negative 1/4 to the n minus 1. And I'm going to set this rule equal to 1 over 20, 48. So first, let's divide both sides by 2. And so we get 4096 equals negative 1/4 to the n minus 1. All right, so I see a base of 1/4, or if you're just looking in the denominator, 4. 4 to the 6th is 4096. So this is 1 over 4 to the 6th. In fact, it could be rewritten as 1 over negative 4 to the 6th, or negative 1/4 to the 6th. So on this side of the equation, I have negative 1/4 to the 6th. And on the other side of the equation, I have negative 1/4 to the n minus 1. Since the bases are the same and the terms are equal, the powers 6 must equal n minus 1, so n equals 7. So now that we know our n value, our a sub 1, and our r, we can write this in sigma notation. So in sigma notation, n equals 1 to 7 of 2 times negative 1/4 to the n minus 1. All right. What about an infinite sum? Well, if I see n equals 0, infinity to 2/3 to the n, you know, this is going to generate our infinite sum. And infinite's different than finite. It's okay to start here with 0 for our infinite sum. And let's see why. If we plug a 0 in here, we get 1. I'm sorry. If we plug a 0 in here, we get 1 times 2 is 2. And then I would have 4/3, and then I would have 8/9, and so on. I see that my r value is 2/3. I see that my a sub 1 is 2. And I know that if I plug in uh, this into the infinite sum formula, a sub 1 over 1 minus r, I'm just going to have 2 over 1 minus 2 thirds, which is 2 over 1/3, or 6. No suffering. So having a 0 down here isn't a problem for an infinite sum. It's only a problem for a finite sum. Okay, well, I think that there's a good introduction to geometric series, or the sum of a geometric sequence. I hope this helps, and I hope you have a wonderful day. Take care, everyone.